I'm Sam Abu-Al-Samad, and this is episode 193 of Wheel Bearings. On this episode, I have a conversation with Danny Shapiro, the Senior Director of Automotive for Nvidia. Did you know you can support Wheel Bearings directly? Head to patreon.com/wheelbearingsmedia, and you can become a patron today. Your contributions will help fund the platforms and tools we use to bring the podcast to you. And exclusives and improvements are already on the way thanks to your generosity. So if you want to be part of an automotive podcast like no other, head to patreon.com/wheelbearingsmedia. So I'm joined today by Danny Shapiro, the Senior Director of Automotive at Nvidia, a company that most people recognize obviously for the video cards that they produce for computers, but Nvidia is a big company that does so much more than just driving your Cyberpunk 2077. Danny, thanks for joining me today.
Sam, it's great to be here. Appreciate it.
So let's start off with a bit of an overview. As I said, Nvidia is best known to the general public as a purveyor of really high performance GPUs for computers, but you do so much more than that. Nvidia is involved in a wide range of things. Can you give us a little bit of an overview of what other things Nvidia is involved in, and then we'll dive into the automotive sector in particular.
That's a really good question. We started out, as you mentioned, as a 3D graphics company creating video cards for gamers. And that was 28 years ago. So a lot has changed in that time. And we're essentially a company that makes accelerated computing solutions. So that's a kind of fancy word, but it means we make things go faster. We make anyone who's doing work with a computer, whether it's a mobile device, whether it's their laptop or a PC or a data center computer, we accelerate the process of achieving their goals, letting them do their life's work. And so this spans across all industries. I mean, every time you talk to Siri or say, "Okay, Google," into your Android device, that goes to the cloud. Well, on the back end is a data center full of GPUs that are using artificial intelligence to figure out what you're saying and come back with the right response. So wherever there's computing, you'll often find NVIDIA at the core of that. In healthcare, we're able to have our processors in medical devices in the hospital. That's helping doctors to analyze x-rays or MRIs or CAT scans. But also in the cloud, they're trained to be able to help researchers develop new drugs and things like that. So this process of using NVIDIA computing for artificial intelligence is applying across the spectrum of industries, from healthcare to energy to finance to manufacturing. There's really no industry that's untouched by this new wave of computing.
Yeah, it's interesting that you mentioned manufacturing. This week happens to be the week of NVIDIA's GTC, the GPU Technology Conference, and one of the things that was highlighted during Jensen Huang, he's the CEO of NVIDIA, for those who don't know, during his keynote was work that NVIDIA was doing with BMW on their plant in Germany where they're building the new iX. Can you talk a little bit about that?
Now, this is a really interesting one in that it merges so many of NVIDIA's core technologies. Again, graphics is a big part of what we do. And so whether it's on the gaming side, whether it's a professional visualization, which is what automotive designers would use to create their new vehicles, it's all done in computer graphics first, 3D models. We do photorealistic rendering. We can do virtual simulations, so a virtual wind tunnel test, or a virtual crash test will be done with NVIDIA technology. But on the manufacturing side, we've worked with them and they've created what's called a digital twin. So a replica of the physical factory, the whole building, the robots, the people, it's all modeled in a virtual world before it's actually built and implemented. And so that gives BMW the ability to experiment how they want to lay it out, how they can optimize the workflows, how they can position different parts of the line to ensure that the workers there do not suffer from repetitive stress injuries and can just do all kinds of streamlining just by dragging and dropping and moving things around and then simulating that versus actually having to build something, test it, and realize, we made a mistake, they have to tear it out and rebuild it. So this concept of a digital twin is very powerful. We introduced something called Omniverse, which is the ability to have people collaborate in a virtual space. So you could have engineers and designers in locations all over the world. And this, of course, was really key during COVID the last year, where everyone was working from home. But these different people could collaborate in this virtual space, work to design a factory, and then implement it in the real world.
Yeah, Omniverse is a fascinating thing because one of the key things about Omniverse, I think, is this idea of having this multi GPU platform, and particularly now with the introduction a couple of years ago of your real time ray tracing technology, and how that enhances the visuals that are created. I mean, in a video game, it makes it look so much more realistic. But for something like simulation for automated driving, that's really crucial to have that realism for the fidelity. Can you talk a bit about how Omniverse is being used in your drive sim platform?
Well, sure. You raise a really good point. Ray tracing, for those that don't know, it's basically having a computer simulate how light behaves in the real world. So you have rays of light that would bounce off of a glass surface and reflect or refract off different kinds of materials, and then eventually it comes back to your eye, and that's how you see. But what we're doing now is physically modeling how light behaves in the real world with shadows, reflections, refractions. And so that technology was first developed, and we worked with companies like ILM, Industrial Light and Magic, Pixar, Disney. All the visual effects companies were really early adopters of our technology in this professional visualization arena. And so now we've brought that into things like manufacturing, where we can create photorealistic models of vehicles. And in fact, most TV commercials that you watch, they're not the real cars driving. They're usually a graphic simulation of that vehicle. It's much more cost effective, especially if it's a new vehicle. They
Wait,
don't want to put
are you
out.
saying that advertisers are? Are you saying that advertisers are showing us stuff that doesn't exist?
Well, or it will exist, or it's just not doesn't exist in that location, right? So you might have a beautiful car that's driving down this curvy mountain road. That mountain road might not exist, but if it does exist, the car, they might not have had their one of a kind prototype in that location. So computer graphics and now ray tracing is used to create amazing effects. And you think about movies, right? So many of these films that look photoreal, everyone's shot along a green screen. So this is where Omniverse comes in. It allows people to collaborate and build these photorealistic scenes and incorporate 3D models from all different sources and work with different software packages. So it's this platform that integrates. So we've extended that with DriveSim. This is our autonomous vehicle simulator. It's an open platform, so we work with all kinds of modeling companies, companies that are developing sensors for autonomous vehicles. We simulate what those sensors can perceive. We also work with companies doing traffic models, environment models, and we pull it all together. And so essentially what we're doing is creating a way to test and validate an autonomous vehicle in a simulated environment before we put it on the road. So the hardware and software that's now sitting in the data center in this simulator is the exact same hardware and software that will actually go in a real vehicle. But this way we can create all kinds of dangerous and hazardous scenarios and test our AV system before putting it on the road. And so we can experiment with different traffic patterns, different lighting conditions, different weather conditions, and we can repeat this over and over and fine-tune all the algorithms, make sure they're much safer than any human possibly could be before we deploy it.
Yeah, and that's critically important because there's out in the real world when you're driving, there's so much variability. Like, as you said, everything from the weather, lighting conditions, depending on the time of day, if there's a little bit of mist in the air or fog or snow, and of course, every vehicle looks different. They've got different surface finishes on them and different levels of reflectivity, and when you're relying on sensors to see the world, I mean, the human brain is remarkable in its ability to adapt and understand the world around it. But it's still a really hard problem for software to interpret the world in the same way that we see it. And I think that idea of really having that fundamental understanding of the way light works, because a lot of the sensors we use, whether you're talking about cameras or LiDAR, are relying on light reflecting off of different surfaces and different surface finishes. And being able to simulate all that, I think, is critically important to getting a simulation that is actually going to be representative of what's happening on the road.
You're absolutely right. And this is a continuous process. So we've developed what we call an end-to-end solution. And it starts in the cloud where data is trained on our GPUs to create these deep neural networks. And a DNN could just be recognizing lanes, or it could be recognizing pedestrians, or it could be reading street signs. And so there's many different DNNs that are running simultaneously in an autonomous vehicle. There's a massive amount of data needed to train that. We're not writing code explicitly to read a stop sign. We feed the system thousands and thousands of images of stop signs, maybe even millions of pictures of stop signs in all different weather conditions, lighting conditions. Sometimes there might be a tree or obstructing part of it. But that teaches the system how to recognize any stop sign then. So that training is done. Sometimes we'll use synthetic data combined with real data, so the simulation can play a role in training. But then once we've developed our algorithms, we're fine-tuning them, we test them in the simulator to make sure then that when we give it all kinds of scenes that it's never seen before, it can still detect everything, like those stop signs, the lanes, the people, the cars. And then if there's issues, we're able to go back and correct, get more data, fine-tune the algorithm, and continue to iterate. Then when it gets to the point that it's safe to put on the road, we take that exact copy of the software and begin our safety tests with drivers and co-pilots out in the real world.
So, for those that are not familiar with some of the AI, machine learning, neural network technology, can you give us a quick high-level overview of what those terms mean?
Sure. Well, there's been a method in the past of writing software, which is sort of a whole series of instructions that you'd get something. And I'll go back to the example of the stop sign. If we wanted to write a program in the past to detect a stop sign, you'd have the front-facing camera of a car generating 30 images every second. And so let's just take one of those images. It's just a bunch of pixels, right? All different color values. And you'd see the scene with the trees and the road and maybe other stuff. And so the computer and the software would have to analyze that entire image looking for what would be a stop sign. And so there'd be all kinds of different parts of code that was written to recognize red, groups of red, detect edges, determine it's a shape, it's an octagon, to discern, okay, there's white and red, and pick out the letters. Oh, it says stop. So there's a huge amount of code that somebody would manually have to write. And then you'd have to adapt it for all these different lighting conditions and weather conditions, and is only part of the stop sign visible. So you'd have to figure all that out. Instead, with deep learning, what we do is kind of leverage the structure of the human brain, which is the model for a lot of this artificial intelligence, and instead have many different layers of processing. And so at the core level, when we feed it an image, it's looking automatically for edges and then determining where those edges are to determine shapes and understanding the color. But we don't actually write code to do this. We feed it information. And so we'll give the neural network a lot of images of stop signs and tell it these are stop signs. So it does the processing to understand that it's a stop sign. And then we may give it a lot of other images and say, these are not stop signs. So it understands what's a stop sign and what is not. And just like a human learns over time and through experience, the deep neural network becomes more and more accurate, more knowledgeable based on more information it's given. So the data writes the software instead of a human. The end result is that we can have many of these DNNs running simultaneously, and they'll have perception that far exceeds the human level and accuracy that's incredible. It requires a lot of processing, though. So that's why the need for high-performance computing is so critical now in the car. First, we would have trained it in a data center, but that data center is not present while you're driving. You just have whatever computing resource is in the car at the time it's driving. So it's processing those video camera images in 1/30th of a second, and needs to identify that stop sign as well as everything else, the lanes, the other cars, the pedestrians. So a massive amount of computing horsepower is now what's critical in these vehicles.
Smartphones have gotten way more expensive over the past decade, and all it takes is one impact on a hard floor to make you wish you had spent a few bucks to put a case on it. Going online without ExpressVPN is like not having a case for your phone, and it only costs a few dollars a month. Nicole, Robbie, and I travel a lot for our work, and we spend a lot of time in hotels, coffee shops, airplanes, and of course the Delta Sky Club. Connecting to the Wi-Fi in any public places with shared Wi-Fi puts your data at risk because bad actors could be intercepting what you send and using it to steal from you. It only takes some cheap hardware to intercept Wi-Fi data, and even a smart preteen can do it. Hackers can make up to $1,000 per victim selling personal information on the dark web. ExpressVPN stops the bad guys by creating a secure, encrypted tunnel between your device and the internet. ExpressVPN uses state-of-the-art encryption that would take a supercomputer up to 1 billion years to crack. I have ExpressVPN on all my devices, including a MacBook Pro, Windows laptops and desktops, and Android and iOS phones and laptops, or tablets. When I want to be secure, I just launch the app, click once to connect, and my data is secure. As I said, I travel a lot for my work, and I have to connect to countless public Wi-Fi networks in many countries. I have ExpressVPN on all my connected devices so that whoever else is on the same network can't see any of my data. That's important because I often have to check banks, credit card accounts, and transmit client data that might be sensitive, as well as filing articles on news that might be under embargo. ExpressVPN protects all of it, and I've been paying for my own account for years. Secure your online data today by visiting expressvpn.com/wheelbearings. That's expressvpn.com/wheelbearings, and you can get an extra 4 months for free. expressvpn.com/wheelbearings. So, what is it in particular about the GPU architecture and the way NVIDIA has done that makes it so well suited to doing these kinds of calculations?
That's a really good question. And yeah, there's many different types of computing in reality, just like you have all different types of algorithms. Traditionally, people were using CPUs, which is the central processing unit. You have that in your laptop or your PC. And the CPU tends to be what's called a serial processor. It does things in sequence, a single order. And now maybe you have a dual core or a quad core, which means you have 2 or 4 sort of computing lanes where you can have data flowing through those and computing on them in sequence. Well, the GPU is a parallel processor. So instead of doing things in a single line sequence, we do a lot of computation simultaneously. And if you think about it, your screen with millions of pixels, all those pixels need to be updated at the same time. So that's why the GPU was initially invented, to be able to parallel process all the data to drive graphics. We've, of course, modified it now for artificial intelligence, which has these same massive computing requirements. And so instead of 2 or 4 lanes like you would have in a dual or quad core CPU, the GPU has thousands of lanes. So essentially now you have a freeway with 1,000 lanes processing all that data traffic. And so we can achieve so much more through parallel processing than you ever could with a CPU. And that's why, because artificial intelligence requires so much computing in such a fraction of a second, that everyone has moved to using NVIDIA technology.
And it's an interesting analogy of comparing it to a highway with thousands of lanes, because just as when we add lanes to a roadway, it automatically seems to fill up with traffic to get congestion back to the levels where it was at. The same thing I think has been happening with the chips that you've been developing for the automotive space. You started off, I think, about 2015 with the original Drive PX platform for this development, and every couple of years coming up with new generations that are getting exponentially more powerful. And talk a little bit about kind of the evolution of what you've been doing in the automotive sector for automated driving development.
You have a really good observation, and I think it's a universal truth about all computing. There's never enough, right? The software increases to the complexity of what the hardware can deliver. Just go back to the original iPhone, breakthrough product, It did things that no other phone ever did. Um, but now compare it to the new generation of iPhone. It's just a world of difference. In each generation, it gets better in terms of the processing and then the software that gets written to take advantage of that processing. So we're absolutely seeing that same trend in the automotive space. We started by bringing our graphics into vehicles a long time ago. And so the infotainment screens and the instrument clusters that used to be very simple, low resolution displays are now beautiful, rich graphics. You look at the new EQS, which was just unveiled from Mercedes, features a pillar-to-pillar dashboard. It spans the entire front of the car. Nvidia drives that, and there's 3 huge displays that are integrated into a single piece of glass. So there's a massive amount of computing just in the dash there. But what we found is as we move into autonomous vehicles, there's so much more computing required because now there's many cameras, radar, LiDAR, that are all generating a massive amount of data that has to be processed in real time. So we're always trying to keep up with the computing needs and delivering what's state of the art. So to go back over time, our first Drive PX, as you mentioned, delivered about 1 TOPS, which is 1 trillion operations per second. So it's fast. And at the time, it was the fastest thing out there. Our next generation, then we kind of were able to shrink that down and put on a single chip. And we did 30 TOPS with our Drive Xavier. And again, that was just amazing. Drive Orin, which is now coming out, and what we just announced with Volvo in addition to Mercedes and many others, NIO, Li Auto, XPeng, a lot of companies in China that are developing autonomous vehicles. That single processor has 254 TOPS, so 254 trillion operations per second. It's just a mind-boggling amount of computation. And finally, at GTC, we just announced this week our next generation we're letting people know on our roadmap. It's still many years out. It'll be really targeting 2025 vehicles, but that is going to have 1,000 TOPS. So each generation, we're able to get these huge improvements. We did like a 25 or so times boost at one point, then an 8 times boost, and now this is a 4 times boost. And so just the computing resource is incredible in our lineup.
And just as a point of reference there, if we go back to 2007 and the DARPA Grand Challenge, the DARPA Urban Challenge, the Chevy Tahoe that the Carnegie Mellon team built up that year and won the DARPA Challenge with, that one had 10 blade servers in the back with x86 CPUs that combined to give about 1.8 billion operations per second. So, you're talking many tens of thousands of times the performance of that pioneering autonomous vehicle, that are coming to cars in production next year, or even the Xavier powered systems, that are out there now. I think that's about 15,000 times the performance of what was in that. So it's amazing to see how that's evolved.
I think for us, what I would comment on though is that people may say, well, why do you need so much? And for us, the number one priority is safety. And so we want to ensure that what is out on the road is safe, is much, much safer than a human. There's so many accidents, injuries, and fatalities that are caused by human error. And so our goal here is to create safer roads. But what happens is we have, part of our safety systems include diversity and redundancy. So there's backups or there's overlaps. We have cameras that are doing processing. There's radar, there's LiDAR in some vehicles, and they're cross-referencing each other. It's like a double check. And if something were to go wrong, in many cases, then there's all kinds of backup systems. If we're trying to take the driver out of the loop, if something happens, we need to have a backup system to continue to operate the vehicle and be able to safely operate it or have it pull over or things like that. So there's the diversity of these systems, and the redundancy also adds to the complexity and requirement for more computing inside the car.
Right, and one of the fundamental changes that happens with vehicles as we move into this area of higher level automation is this shift in mindset. When I was working on stability control systems and anti-lock brakes, we would design fail-safe systems that would detect a failure within the system and alert the driver that, okay, this system's no longer working. But now when you're talking about a vehicle that may not have a driver, may not have a human on board at all, if it's a delivery vehicle, for example, fail-safe isn't good enough. It's not just a matter of detecting the failure, but it has to be able to detect it and then continue to operate even if in a reduced mode. So you're talking fail operational, which is why you need that redundancy and diversity and doing things in different ways.
That is so true. And I think what we see is that it might not be a full duplicate system, but it is a system that, if something were to happen, a sensor fails perhaps, or there's some other issue, the backup system doesn't have to do everything, but it needs to be able to navigate the vehicle pulling over safely and summoning assistance. You also see this in teleoperation, which is kind of remote control of a vehicle. So an autonomous vehicle may find that it gets into a situation where there might be a delivery truck that's blocking traffic, and it may need some kind of human intervention. And so the car would call back to the command center, and a human could then basically teleport into that vehicle and see through the sensors on that vehicle that, this delivery truck is blocking, let me turn around, or let me then maybe cross the double yellow to pass it, or do some other things that may not be built into the system. And so then we can navigate around that issue and then send the autonomous vehicle back on its way. So I think we'll see a lot of teleoperation. There's a lot of startups that are doing really interesting work in that space. And the integration of the cloud to the vehicle will become more and more a part of this solution. We see the data center managing a fleet of vehicles, and each manufacturer basically having their operations center. It's not just about a single car, but rather this huge opportunity of maintaining fleets. And to that end, there's going to be software updates, of course. So the ability to monitor what's happening in their cars, to collect data from their cars, to improve the software, and then go back over the air, do software updates, is this whole notion of a software-defined car. It's not fixed function elements in the car, but rather a full computer at the core with a car built around it. And that car gets better and better over time.
Yeah, that's that's an area that Tesla pioneered in part with help from Nvidia. They used a lot of Nvidia processors in those early Tesla Model S's and Model X's, and the idea, in the past it's always been manufacturers would design, develop a vehicle, sell it to consumers, and then the manufacturer moves on to developing the next generation of that product, and that product that the consumer bought, unless they did aftermarket changes, it stayed basically static for its lifespan. And that's no longer the case. We're getting to the point now where new functionality can be added at any time. And, as an example, this week, Ford talked about rolling out their new Blue Cruise hands-free driving system, later this summer. And Tesla has obviously updated their software repeatedly over the years, and that's going to be a standard thing going forward, I think, for pretty much everyone, isn't it?
Yeah, you're right. I mean, if you think about it, whether you have an iPhone or an Android phone, you get regular updates, and that's the norm. It's hard to imagine going back and buying a flip phone or some other device that doesn't get updates. Why would you? And this is really becoming the trend with cars, having this core computer, centralizing the computing. There may be 100 different chips in a lot of cars today, and the complexity is too great. And also they're fixed functions, as you mentioned. So the ability to have this central computer that's updatable to control how the car drives and drives itself in some cases, but also everything down to the instrumentation, how that could be customized, how the door locks work, how the windshield wipers function, all sorts of things can all have different modes and preferences when it's software controlled. And so for me personally, I've been driving a software-defined car for nearly 5 years now. I can't imagine buying a new car that doesn't get software updates to make it better. And I think once you experience something, whether it's particular safety features in your vehicle or this ability for the whole driving experience to be updated, it's really hard to go back and give those things up.
Yeah, definitely. So one one area you mentioned, you talked about data centers, and that's actually something that's coming more into the car itself. You also mentioned Atlan, one of the interesting new components, and all of these chips, from Xavier, actually going back to the original system chip, in the Drive PX, and I'm sure further back than that, is these all contain multiple kinds of processors in them. They contain GPU cores, but they're also ARM cores and tensor processing units for AI acceleration. But Atlan has a new piece in there, this Bluefield 2 DPU. And tell us why that's important.
Yeah, so you're right. The SoC, there's a lot of acronyms, so I'll try to clear them up. SoC stands for System on a Chip, and that integrates many different types of processors. It has a CPU, which is the central processing unit, the GPU, the graphics processing unit, a DLA, which is a deep learning accelerator, a PVA, which is a programmable vision accelerator. And so there's different types of data coming in, there's different types of algorithms, and so they each are processed on different parts of the chip that are optimized for those operations. Cybersecurity is a huge factor now, huge issue in the data center as well as autonomous vehicles. And so we've been developing networking technologies to secure systems. And so again, the types of systems that are used in data centers for maybe banking or medical records or all kinds of other data processing have technologies for encryption and virtualization and firewalls and authentication to make sure that code that's running is safe code and is authorized code and there's no intrusion. So what we're doing now with Atlan is bringing our Bluefield data center or data processing units into the chip itself. So rather than having to have a separate element on our drive platform, it's now integrated at the chip level and designed for higher bandwidth. So we see more and more sensors, higher resolution sensors on these vehicles, and they generate so much data that the infrastructure inside the car is struggling to handle it. So we're bringing Ethernet into the car and right into the chip to be able to process massive amounts of data. This traffic, these thousands of lanes of data I was talking about are traveling over Ethernet, and so there's essentially data center caliber technology inside the car. So these future vehicles will truly be data centers on wheels, not just an iPhone on wheels, which was sort of the analogy of the past, but it really is now becoming a data center on wheels.
Yeah, and with things like your Hyperion 8 platform for development, which combines a suite of sensors and the Orin computers and your software. I think that if I recall, that one has eight megapixel cameras as part of it for long range, and then also some shorter range cameras and interior cameras, and that's a lot of data to be chunking through every 30 milliseconds or so.
That's right. So we have basically it's a whole development kit. It's an out of the box. So you have the sensors with cameras, the radar, the lidar. It's all calibrated. There's the data recorders. There's cabin monitoring, and so our customers will take these systems, put them on their vehicles, and right out of the box have an operational data collection vehicle and a development tool. So they're able to start using our software as well as building their own applications on it, and it really accelerates the process of getting vehicles on the road for that whole development cycle. And complementary to that, it's already all built up in the simulator, so they can be essentially testing everything right away before they even put it on the road.
Well, Danny, I want to thank you for your time. You have any final thoughts you want to share?
Well, appreciate the invitation to be here, Sam. And I think this is a really exciting space. It's not a simple task. It's perhaps one of the most challenging computational tasks in the world, trying to replace a human in a vehicle. And it's also a safety critical aspect of what we do every day. So while AI is being used everywhere, and as we talked about, in healthcare and in finance. Companies like Netflix use artificial intelligence to help recommend a movie for you to watch based on your likes and dislikes in the past. But if they recommend something that's not exactly right, if there's a bug in their software, it's not a big deal. What we're talking about here with autonomous vehicles, safety is critical, so we have to ensure we get it right. And so that's why you see it potentially taking longer than people initially projected. It's a very complex process. We want to make sure we get it right. We're working with amazing companies like Mercedes-Benz and Volvo Cars and many, many others to develop this technology that's coming into passenger vehicles. We're also working with companies like Cruise and Zoox who are developing robo-taxis, and companies like Navistar and Too Simple that are doing trucking and last mile delivery. So there's going to be so many different types of autonomous vehicles that the public will interact with and get to experience. And just over the next several years, we'll see more and more of these going out into deployment. Might not be on your neighborhood streets, but first on highways or geo-fenced limited areas. But the technology is coming and will be a safe rollout. So we're really excited to be at the core of this transformation of the transportation industry. And to say stay tuned, a lot of great news to come this year and next.
Thanks. And my 30 years in this industry, this is definitely the most interesting time, and more things changing faster than ever. So thanks, Danny. Appreciate it.